now we have looked at a couple of definitions of stability. Stable, it's the response approaches zero as time approaches infinity. Okay. If you look at this is a response and this is time scale response. System could respond something like this. Okay. Or you can look at, so this would be, this would also be an exponentially decaying response. On the same lines, if the response of the system is approaching infinity, as time approaches infinity, then it is unstable. Okay, so if you're looking at something like this, then this is a unstable system. This is a stable system. And something like this is a marginally stable system. And this is one of the definitions, and the other definition we looked at was poles in the S-plane. So if you're looking at, this is your S-plane, this area corresponds to stability. Any poles in the left half plane means the system is stable. Okay. Any poles on the imaginary axis means the system is marginally stable. And this area corresponds to unstable systems. There is another technique to determining stability. It is called Routh-Hurwitz criteria. Okay. So we'll look at this Routh-Hurwitz criteria. context of an example. So here the question would be, is the above closed loop system stable? So the first thing you need to do is you need to determine T of S, which is G of S over 1 plus GS Hs, right? This will be over S cube plus So this is your closed loop system, okay? Once you have the closed loop system, if you just find out the roots of the system, you'll know whether the system is stable or not, okay? You do a roots command in MATLAB and you'll figure out if the system is stable using either this one. How do you figure out if this system is stable or not using something like this? You do a step plot, function of a step response, and see if the response is diverging, converging, or oscillating. In this, what you do is you construct something called route table. Okay. So how do you construct route table? Okay. The route table will be something like this. The first column would be the coefficients or the power of S's. Okay. What you do is you look at the polynomial. So the polynomial here is a third degree polynomial, right? S cube. So you start with S cube, S square, S1 and S0. You populate the first row of this table with the coefficients of odd number of polynomials. So you have S cube S, right? These are the odd polynomial degrees. The coefficients for them are 1 and 31. And the second row is even numbers. Okay, so it is 10 and 1, 0, 3, 0. This is always the first step for constructing the Routh table, regardless of what degree polynomial you are dealing with. If it's a fourth order polynomial, you would have done S4, S3, S2, S1 and S0, and you would populate the first two rows that way. Got it? Now you need to figure out these two elements. Huh? Odd powers. So odd powers and even powers. If it's an even powered polynomial, you start with even. If it's odd, you start with odd. The first two rows are always pre-populated. Okay. Evens first and then odds, right? Okay. And then you have, so this element is this minus this over this. So it's, the first thing you need to do is, if you find something like this, you look at the rows, it will just make things simpler for you. So what I did was, 10 is common in that row. So I divided the entire row by 10. Okay? So this element now would be this into this minus this into this over this. It's always like that. Huh? If it is cancelled, it is over 1. Okay? So if you take 1030, it was 10. If you take 103, it is 1. So, okay. So this is 103 minus 31 over 1, which is it's 72, right? And similarly, this element would be you have 0, 0. Since there is nothing over here, now you do, again, this minus this over this. It would be 0. Right? And similarly, now this element would be this minus this over this. Sure. So S, let me write this down, then I'll give you the formula, okay? So you have, this is 103 and this is 0. This is minus 103. So S11 is equal to S31, okay, into S22 minus S21 into S32 over S21. This makes sense? S31 is the first element in the third powered row into second element in the second row, second powered row, minus this, which is the first element in the second order polynomial row into the second element in the third order polynomial over this. Got it? Make sense? So this pattern continues. This one? So you assume zeros here. Yeah. Okay. Because there is nothing over there, you can take that as 0. So once you take that as 0, this would be 0, this would be 0. Now you do this minus this over this, which is minus 72. Okay. This, the first row, this, the second row. And then the entire thing was divided by 10 to make it simple. Okay. It's actually minus of this. So this would be minus, this would be plus. So it's minus. So it would be minus of entire thing. Okay. So if you do this minus this, or you can say this minus this over this. Okay. So it would be minus 72, and then you're going to get this. This is 0 minus rent. So now once you have constructed the route table, the rule is number of poles in the right half plane is equal to number of sign changes in the first column. Okay, so you look at this. From this element to this element, does the sign change? No, it does not, right? From this element to this element, it changes. From this element to this element, it changes. So how many sign changes are there? Huh? 2 sign changes. You just told me 2 sign changes. From this to this, this to this. 2 sign changes. So that means number of poles in right half plane is equal to 2. It's unstable. That means it's unstable. So for no sign changes. Right. So if there is any sign change in the first column, that means that the system is unstable. Okay. The advantage with something like this is you can automate this process and immediately tell whether the system is unstable or not. for larger system, this is very useful. There are a couple of special cases for this system. The special cases are something like this. You can see here that any of the elements in this, in the first column can go to 0, right? You realize that? This could be 0. For example, if these two are equal, then this could be 0. If the product of these two are equal, this will be 0, right? Because this minus this. So what happens to this element then? Huh? It would be infinity. It would not be undefined, because it would be this. It would be undefined, yes, because it is 0 over 0. It would be this over this, which means 0 over 0. It is undefined. So in that case, we cannot really say the system is stable or unstable based on that value. So what do you do? We do something called Epsilon method. In the first column has a 0, we use the Epsilon method. Again, we'll take a look at an example how to do this. The example would be over All right, tell me the route table now. How do you construct the route table for this one? Right. So you have S5, S4, right? So what you do is you pre-populate only these two, the first two rows. So what are the pre-populated rows? 1, 3, and 5. And this would be 2, 6, and 3. now your S3 would be what? What would this element be? With 0, right? And so this element would be 30 minus 9 over 6. See that? 6 by the 30, 9 over 6, 21 over 6, right? This would be 0. This one? Oh yeah. You have 2, 6 and 3, right? So this is considered S0, right? So you have 6, 5 minus 9. Over 6, right? It is always this or minus of this minus this over this. Over this. So if it is this element, it would be, if you're talking about this, it would be minus of this minus this over this. This is for the S11. This remains the same. Okay. So now what we do is we replace this 0 by a very small number called epsilon. Yes. Huh? So this is what we said, right? If you're looking at, let me name this. Let's say this is A1. So let's name this as A5, A3, A1, A4, A2, A0. Okay. So you have, let's do B, B3, B1, B, you don't need this. So B1 would be minus of A3, A0 minus A2, A1 over A2. You see it? Now, or you can just write this as A2, A1 minus A3, A0 over A2, right? A2, A1 minus A3, A0 over A2. That is what you get, 21 over 6. Okay. So you have S2. Now this would be six epsilon minus 21 over 3 over epsilon. Okay. This would be 3. This would be 0. S1 would be 21 21 over 6 into 6 epsilon minus 21 over 3 minus 3 epsilon over epsilon. Okay, this would be 0 and 0. And finally, it would just be this thing again. Epsilon, yeah, it's small e. This one? When it is 0, you replace that by epsilon, a very small number. Okay, so here it is 3, 5. 0. This one? It's so it's this 6 epsilon minus this would be 21 over 3 4 epsilon. Okay. So you think about this now. When you have something like this, if epsilon is a really small positive number, okay. If it is negative number, the system is unstable, right? Because from here to here, the sign will change. If it's really small positive number, this would be negative, right? It again is an unstable system. So whether you approach it from, so for example, if this is negative, this would be negative, right? This would still be negative. Or this would be positive. This would be positive actually. Right. Okay. So whether you approach it using a small, very small positive value of epsilon or negative value of epsilon, you will know whether the system is stable or unstable. Okay. So for example, this would be from here to here for positive epsilon, this would be unstable. Which one? This one? No? Right. If I did this, it would be negative. If I did this minus this, then it would be negative. So you see, this follow this. Negative of A3, A0 minus A2, A1. So if I reverse it, it will be this minus this. Okay. So here, with substitution of epsilon value, we can figure out whether the system is stable or unstable. And when I say substitution, you approach it from really small positive value of epsilon and really small negative value of epsilon. All right. When you do, this is a very simple, very straightforward method. It's just a matter of following a process. all you need to do is, if you're given something like this, you need to first figure out how to get to this. Okay? Once you figure out how to get to that, then you do a route table. Okay? If you know how to do the route table, you'll immediately start figuring out whether the system is stable or unstable. So for your next exam, you would have chapter 5 and this one, and possibly stability as well. This is stability. We'll probably do steady state error, which is chapter 7. There is not much in this chapter left. There is one more case which we'll do. If one of the rows is completely zero, then that is also a special case. So we'll do that, and that is it with chapter 6. And chapter 7 is steady state error. Steady state error is it's not complex, but there are a lot of things to make sense of or recall. So I want you to attempt chapter 7 as part of your exam, next exam, so that it is easier for the finals. I'll have your test ready tomorrow, but I also have to submit your grades for tomorrow. And if you want to take a look, come to my office tomorrow morning. You can take a look. Yes, sir. Huh?